Okay, as I was saying, it was a bit longer presentation. We just need to shrink a little bit, so it will be just a summary, an overview of C++ threads. Okay, let's start from the beginning. So before C++ 11, you didn't have the support of multi-threading officially, let's say, in a native way in C++. Of course, we have multi-threading support with other libraries. I guess you have some experience with OpenMP or maybe Boost, so you can still do multi-threading in C++, but not with the, let's say, staying inside the language standard. Starting from C++ 11, then we have the support for multi-threading, which means that we have objects to represent and manage threads, shared data, with shared data protection and thread synchronization and so on. So I will give you a quick overview of these objects and how they work. And one thing that you have to know is that this standard doesn't specify how these threads are implemented. This object, let's say, this support for multi-threading is implemented, which means that even if you're doing multi-threading in C++ within the standard, using the C++ object, and you're still using a multi-threading library on your system, like, for example, pthread for GCC or Windows threads or whatever. So, as you can see from the make file in our examples, we see that for this multi-threading example, you will have this flag at the end of the compile command, which means that we are using the pthreads support for C++ multi-threading. So how we represent a thread in C++? Now there is this object, which is as you can imagine, is the standard thread object. It's a class that represents a thread of execution. You can create in your main function a thread like this. You have to invoke the constructor of the thread, which is this one, and you have to provide to the constructor what is called an initial function, which is something that represents the task that you want your thread to complete, basically. In this simple example, you have as initial function this hello function that does nothing but printing, of course, as usual, the hello world function. And then you make a call to the tjoin method that we will see in a while what is doing. Let's go ahead quickly. So when you start the main function, we have already one thread that is running, which is, let's say, the main thread, the thread that is executing as initial function, the main function itself. Then at this point, when you create a new thread, you're starting a new thread that executes the provided initial function. And then at this point, you make a call to this join function that is a blocking function that makes the calling thread to wait here for the execution of the provided function to complete. So in this case, will be the provided function is super quick, is doing nothing but printing a string. But in more realistic case, you will have some real work to do. So it may be that your calling thread will wait here for a while. Quick look to the thread constructor. You can see that there are, let's say, two arguments. Is more one argument and then a parameter pack. The first one is a function that can be any callable object, like a function, an object providing the operator method, or can be a lambda expression. That is the way that is a way to specify the work that must be done by the thread. And the second argument, this parameter pack, is the set of arguments that must be passed to the function itself.
Quickly, you can note these R-value reference stuff that is implemented with the perfect forwarding that we've seen.
Okay, so talking about the thread management, every time that you create a new thread in your code, you have two possible management strategies. The first one is the one that we've seen in the initial example, that is the one related to the join method, which means that the calling thread will wait for the other thread to complete the work, and it will stop there because this is a blocking function. The second possibility is to make a call to the detach method that instead sends the thread in background, and it detaches completely from your main thread of execution, which means that you have no way to communicate with that thread anymore. So you have these two possibilities when you create a new thread. Okay, as I've already said, you have the possibility to pass some argument, to pass a list of arguments to the thread constructor that will be forwarded to the function. This is another very easy example where the function is taking an integer, a string, and a double, and you can do something like this in the thread constructor. You pass the function, and then the list of parameters that will be forwarded to the initial function. One important thing is that all the arguments that you are passing to the thread constructor are copied to the stack of the new thread of execution. This means that if you have something like this one, let's say that you have this setX function that takes in input an integer and then an object of type X by reference and is doing something like this. So it makes a call to a non-const. Let's assume that this is a non-const method of the X object. So you're trying to modify this parameter within the function. This is something that you can do if you're running just one thread. You make a call to the setX method, passing the X variable, and then you will see that your object is in a modified state when the function has been executed. You cannot do something exactly like this with the threads because this X variable will be copied to the stack of the new thread. So it will be a copy, not exactly the same object. So when you will do something like this in the main function, you will pass the object X and the setX method, setX function. After the execution of the thread, after the call to the join method, your X object will be not modified because it will be in the original state because the variable is copied in the stack of the new thread. It is not called by reference, basically. You can still force a call by reference specifying what you want to do using the standard ref function. In this case, you will be really passing the object by reference to the initial function of the new thread. Something about the resource ownership. This is something that we have already found for example, in the presentation about smart pointers. In this case, the resource, we are talking about resource ownership again, but in this case, the resource is the thread of execution. You can imagine it as the thread that is really executing on your system and that is doing the work that you provide with the initial function. In this case, the resource ownership is implemented following the unique ownership semantics, which means that each thread can own there is just one thread, no more than one thread that owns a given thread of execution at any time in your code. So there is no shared ownership of the thread of execution. So it's like the unique pointer where the resource is dynamically allocated memory, and which means that the copy constructor and assignment operator of the thread object are deleted. So it is a move only type. But you can still move the owner, the thread of execution using the move semantics and doing something like, you cannot do something like this, but you have still move semantics, and which means that you can do something like this. You can create a first thread, providing as an initial function this function fun, and then you create a new thread of execution. It is default constructed, and then you can move the ownership between the. This is a new function of your pointer, but yeah, but well, it doesn't matter.
Twice clicking, and then you.
Oh, this is nicer. I prefer this one. So again, then you can move the ownership of the thread of execution from T1 from T2 using the standard move function. At this point, you can join the T2 thread because now it's T2 that is the owner of the resource we are talking about, which is the thread of execution. I will go quickly. Maybe this is not interesting. I just say that if you have experience with OpenMP or MPI, even I think is the same. In MPI you have multiple tasks. In OpenMP you have multiple threads. But anyway, you have an ID, an integer that identifies uniquely all the threads or all the tasks. There is something similar also for the C++ thread. But even if they look like. It looks like more or less an integer, but it's not really an integer. It's a specific type that is defined as a standard thread ID, that can be used to identify the single threads, but has no semantic meaning, which means that you won't see a list of threads with the corresponding ID, which is 0, 1, 2, 3, and so on. You will see, let's say, strange numbers that have no semantic meaning, but still can be used as, let's say, for debugging, and they have all the comparison operator, which means that you can do something like this. You can get the ID of the current thread. You can get the ID of another thread that is running, and you can check if they have the same ID. And then you can even print this number, but you will see, as I said, some strange numbers. But still, they can be used for debugging reason if you need to check anything like this.
There is a little thing here, the fact that the thread IDs can be reused. So if you have a thread, you destroy the thread, you create another thread, they might share the same ID. So even checking that the two thread IDs are the same, it doesn't imply it's the same thread. So it's really tricky to actually use.
Yeah, let's go ahead to data sharing. I think that we need this one for the exercises. So let's have a quick look to this example. I have this initial function that I will use for my thread that is doing nothing but taking an integer in input and updating the value. Okay, so I'm starting assigning initializing this variable to 0, and then I will pass the variable and the function to the thread constructor for these T1 and T2 threads, and then I will make a call to the update function also in my main thread. So there will be 3 calls to the update counter. They are all working on the same input-output variable. They are all trying to update the variable itself. And then I will join the two threads. So the question here is, at the end of the execution, what will be the value of the counter variable itself? And if you have some experience with multi-threading stuff, you know that here you have a data race condition, because you have multiple threads that at the same time are trying to update the same variable. They're accessing the same variable in write mode. And this is the origin of the data race condition. In order to avoid this situation, you need to make the region of code where you are updating the variable critical. If you are using the same terminology of OpenMP, for example, which means that you need to have that region to be mutually exclusive in terms of access, which means that you can have only one thread at any time that is entering that region. In this case, you are serializing the execution of that part of the code. You will be sure that you will not have this data race condition. You can do that with the C++ threads using this object, which is the mutex object, where mutex means mutually exclusive. And you can make that particular region where you are updating the variable, where all the threads are trying to update the variable, you can make that region critical doing something like this. You create the standard mutex object, and then you start the critical region making a call to the lock method, and you end the critical region making a call to the unlock method. Everything between the calls to a lock and unlock method will be critical, which means that only one thread will execute at any moment this part of the code. And this will avoid, of course, any data race problem. When you make a call to the mutex lock method, and we say that the mutex owns the lock starting from that point on. Okay, in this case, we have again another, let's say, another resource which is owned by something, like for the resource ownership of smart pointers. In this case, the resource that is owned by something is the lock on the mutex. This is important because here we have another example of implementation of the array idiom that we have already seen for smart pointers, and it is represented by the lock guard method. So this is just an update of this function. This is the original function where we create the critical region. This is an update of this function where we are using this lock guard object that is a template class that takes as a template parameter the mutex type, and there's a constructor that takes in input the mutex that we want to lock. So this is an implementation of the array idiom, as I said, because When we create this local variable, we take the ownership of a given resource, which is in this case is the lock on the mutex. Starting from this point on, all the code that will follow is critical. It's like having the code between the lock and unlock method. And following the RAI idiom, when the local variable, which is this lock guard object, is destroyed because it goes out of scope at the end of the function, the resource, which is the lock, will be released automatically for you. So it is like, if you use this mutex lock and unlock, it's like doing new and delete for dynamic allocation. If you do something like this, it's like creating a unique pointer that takes the ownership of the resource and release the resource when it goes out of scope. Yeah?
Is there any other advantage to the use of the lock guard, other than like we have a way to have two lines, mutex lock and mutex unlock?
With lock guard, basically you don't have any possibility to forget to release the lock, of course, because it is done automatically for you. With the mutex, you have to do that. You have to remember to do the unlock step. And of course, the problem with the lock guard is that you have more, let's say, it's easier to be used because you have no possibility to forget to release the lock. The problem is that you are losing something in terms of lock granularity, because everything starting from the line where you create the lock guard to the end of the scope, everything will be critical. Which means that if you need to limit the lock guard starting from let's say a given line to another line, you're not able to do that, because the lock will consider everything to the end of the scope.
But you can use also additional scopes.
Yeah, of course. Or the other possibility is using the unique lock, which is something in between directly using the mutex lock and using the lock guard, because unique lock here, when you create a unique lock object, you're doing something similar to the creation of a lock guard, because this constructor will take the ownership of the lock on the mutex. So everything starting from this line, let's say, will be critical. It will be critical to the point where you make a call to this lock unlock method, which is similar to the mutex unlock method. So this is something the unique lock is in between, let's say, with respect to lock guard and the mutex. With the mutex, you have to make a call to lock when you want to start the critical region, and you have to make a call to unlock when you want to finish the critical region. With the lock guard, everything is done for you, because when you create the lock guard, everything starting from that point on will be critical. And then you don't have to deal with the unlock step. With the unique lock method, is like creating a lock guard, because this line will be critical, but then you don't have to wait for the unique lock to go out of scope for releasing the lock, because you can manage that release making a call to the unlock method. Okay, we have some layout problem here, but just let's have a quick view of the unique lock basic API. These are the three possible way to construct a unique lock. As you can see, it is taking the first argument is the mutex, where the lock will be applied, and then you have three possible execution policy. Let's say three possible way to operate with the lock on the mutex itself. The first one is a defer lock, which means in this case, you are not trying to acquire the lock on the mutex. You just create the unique lock object, and then you can make a call to the lock method in a later point on your code. The second case is the try to lock. With the try to lock flag, it means that when you create the unique lock, you will try to acquire the lock on the mutex. But if you can't do that, because there is already another thread that owns the lock on the mutex itself, the execution of this constructor is not blocking. It will continue. And then you have the last case where you assume that the thread that is calling this constructor already owns the lock on the mutex. So you will just acquire an existing lock on the current mutex. As you can guess from the name, it is a unique lock. So usually when you have a unique it means that this type is not going to share the resource it is managing. And this is also the case for the unique lock, because it means it is a move-only type, so you cannot copy construct and move a unique lock. So you can only using the move semantics with this type of lock. Yeah, nothing relevant. You can just check if your current unique lock is owning the lock ownership. There is one method interface which is owns lock, and it will return true if the current unique lock is owning the lock on the mutex. Otherwise, it will be false. So nothing special here. Yeah, the idea of a unique lock is more or less the same of the unique pointer. It is just kind of a wrapper around a mutex object that forwards all the calls to the underlying mutex, which means that it is just a kind of a mutex lock with an additional flag that checks, that tells you if the current mutex is owning the lock or not. And of course, you have some performance penalties because you have more flexibility, but of course you have this extra flag that is part of the object. Do we need async future? So I don't know how much time do I have.
Okay, if you want, you can have like a few minutes, or we can make it later if we need. Your choice.
Whatever. I mean. Okay, so we can go on then.
Okay.